Tonight we're going to be expanding a little bit more on Lewis dot structures, and we're going to be talking about this thing called resonance and formal charges. So what the heck is resonance? Well, some Lewis dot structures actually have more than one valid one that actually works. The rules for a Lewis dot structure, whether it works or not, is that the number of valence electrons adds up, so you don't somehow gain or lose these electrons. And then the other thing is that everybody follows the octet rule. Okay, or duet rule for hydrogen, or if they have an expanded octet, then they follow those rules. What actually exists is that the Lewis dot structure is an average of these resonance structures. What that means is that it's not exactly even necessarily as far as how stable they are or how favorable they are. Some structures last a lot longer than others, but all of them are valid as long as they follow these two rules of the valence electron and octet. What happens is that the electrons are really delocalized, and what that means is that they can move around the entire molecule. The electrons can move. That being said, the arrangement of the atoms still stays the same. So when we're looking at the structure right below, if you look at nitrogen, nitrogen is always in the center and the oxygens are always on the outside. The nitrogen doesn't move positions. And the other thing is that the overall charge of the system must stay the same. So if you had a -1 charge, then you need to remain a -1 charge. Now, looking at these are three different resonance structures of the nitrate ion. Notice that the N is always in the center. Every element has an octet, so they're happy. You always have this -1 charge. How you show the resonance structures is that actually you draw these arrows, these double-edged arrows, and what it's doing is it's saying that these structures are going back and forth. These electrons are moving constantly back and forth. How does it do that? Well, if you look at the first one to the second one, we have this double bond. What happens is that the double bond moves, okay, to make the lone pair, and then the lone pair of the oxygen then moves. So notice that they're continuously moving. And then in the next case, from 2 to 3, it'll move up, and then this lone pair will move down. So they're constantly moving these electrons, and that's where you get your three different structures. So drawing a Lewis dot structure for each of these individual molecules, we've got CO, carbon monoxide, and this is actually the only structure that can be made. There are no other resonance structures, okay, using the 10 available electrons or 5 bonds. You can't create something else where they also complete the octet rule. Okay, then we've got CO2. If I draw a normal CO2, typically this is what I get, where there's 2 double bonds and 2 lone pairs on the oxygens. Why? Because we have a total of 16 electrons, which means 8 lines. Okay, but this is not the only actual structure. What can also happen is that this double bond moves, and instead of making a double bond, it actually forms a triple bond between the carbon and the oxygen. When that happens, the oxygen on the left will lose a lone pair, and the oxygen on the right will actually gain a lone pair. That being said, you can also do the reverse, where the oxygen on the left has a single bond to the carbon, and the oxygen on the right has a triple bond onto the carbon. And then once again, the 3 lone pairs on that left oxygen. OCN does a very similar kind of structure. So you've got O, which is double bonded to C, double bonded to an N. Lone pairs on both of those with brackets and a charge. Why I'm using brackets and a charge is because it has a charge of a -1. That also will move these double bonds. So if we're going to move this oxygen to make a triple bond, then that bond will make a lone pair. Okay, and then they'll keep moving around. So you get a very similar structure to the one above, just with different elements. Brackets, charge, double-edged arrow, and then the last one is where you have those 3 triple bonded to the N, brackets, charge. So these are just showing how they have different resonance structures. Now, how do you determine which resonance structure is the most favorable, meaning the most stable? Okay, because not all of them are equal in stability, and they always want to go to the most stable. The atoms and the molecules are always trying to make their formal charge or their overall charge to be as close to 0 as possible. So the ideal is where everybody has a 0 charge. But if there is a negative charge, they want the atoms want it to be on the most electronegative atom, which makes sense because they would want to be gaining the electrons as being electronegative. They love having those electrons. So there's a simple formula that you have to do. All it is a comparison between the number of valence electrons that it has, that the element has when it's by itself, and then what you do is you add up the total number of electrons it has in the Lewis dot structure itself. And it's just a simple subtraction problem. Okay, these are the rules though. If you have a lone pair, it is entirely on the atom in question, meaning if you have one lone pair, there are 2 electrons counted for this part of the equation. Whereas if you have a shared electron, meaning a bond, like let's say O to C, I would only be able to count half of that, which would mean it would have 1 electron. So for every bond, you get 1 electron. If you have a double bond, that would be 2 electrons going towards whatever element you're trying to find the formal charge for. So let's try to do POCl3. So if you look at CLs in all of these cases, they all have the exact same number of bonds. They all have the same number of lone pairs. So if I find one, I found all of them. Okay, so what I'm going to do is find one. So Cl has 7 valence electrons, and in this structure, it has 2, 4, 6 electrons coming from the valence electron, or from the lone pairs, and then it has 1 from that single bond. So that would be a total of 7. So its formal charge is 0, which means that all of these guys are also 0 with the Cls. Now in relationship to the oxygen, oxygen has 6 valence electrons. So in this structure though, as the Lewis dot structure is 2, 4, 6, 7. So what its charge is a -1. So its formal charge on this oxygen is a -1. Phosphorus typically has 5 valence electrons, but in this case I count all 4 single bonds and 0 lone pairs, so that represents 4 electrons it has, which means it has a +1 charge. Now if I were to focus on just the charges, the formal charges, my individual components should add up to be my total charge of my compound. If I look at my total charge of my compound, I don't see 1, so therefore they should cancel each other out and be equal to 0. So the chlorines are all contributing zeros, so that's nice. The P has a +1 and that oxygen has a -1. So +1 and -1 equals 0. So overall my net charge is 0, which means that this Lewis dot structure and the formal charge calculation is probably correct. All right, so let's just try to figure out the formal charges on these guys. Once again, all of these oxygens have the same structure. So the oxygen has 6 valence electrons. In this case, it has 2, 4, 6, 7 electrons. So that means that each of those has a -1 charge. In the chlorine, we have chlorine typically has 7, but when you count how many electrons it has in this Lewis dot structure, it's 2, 3, 4, 5. So when you subtract that, you get a +2. So in this case, chlorine has a +2 charge. If you add up all your charges, we have -3 from the oxygens, the +2 from the chlorine. So overall, that is a -1, which is the charge of the overall compound, so we're good. Trying to do this guy, the CHO2 minus. So oxygen in this one right over here has 6 valence electrons. Counting, it has a total of 7 electrons, so its charge is a -1. The oxygen on the top has a total, once again, of 6 valence electrons, and it only has 6 electrons, so its formal charge is 0. Hydrogen has 1 valence electron. It is sharing that 1, or the 2 electrons, so it has 1, which means its formal charge is 0. And carbon has 4 valence electrons. It is counted as having 4 electrons, so therefore it has a formal charge of 0, which means 3 zeros and a -1 equals that -1 charge. CO2. So in this case, carbon has a formal charge of 0 because it has 4 and it only has 4, so that would be 0. Oxygen on the right has 6 valence electrons. It personally has 5. So that means it would have a +1 formal charge. The oxygen on the left has 6 valence electrons originally. It, as drawn, has a 7, so you have a -1 charge. -1 and a +1 equal an overall charge of 0, which matches that. And then your final structure, this chlorine has 7 valence electrons. As drawn, it only has 6, which means that it has a +1 charge. This hydrogen has a 0 formal charge. Carbon has a 0 formal charge. All of these hydrogens have a 0 formal charge. The only one that also has a different one is this carbon, which has 4 valence electrons typically. And as drawn, it has 2, 3, 4, 5 electrons, so therefore it is a -1 charge. So a -1 and a +1, they cancel out to be 0. All right. So what does this mean? Now I know that resonance structures exist, and I know that we can calculate these formal charges. Well, what you do is you calculate all these formal charges, okay? And then you follow these 3 steps that are down here. So the structure that has the max number of atoms with full octets will be your most favorable. Then what you're going to do if somebody does have a formal charge, if the negatives is found on the most electronegative element, that would be the second most favorable. And then the last one is it's where there's the least number of formal charges written. That would be the third most favorable. Okay, so looking at this, when we're trying to rank these, what you want to do is you want to do the formal charges. So calculating it out, I have a +1, I have a 0, and I have a -1. If I did the formal charges on this guy, I have 0, 0, 0. So looking at this, following step number 1, this structure on the right has the most number of atoms with the full octets and also the least number with the formal charges. All of them have 0, whereas this one has 2 with formal charges. So even though both exist, the one on the right is definitely more favorable. Looking at this structure, okay, looking at the formal charges, 1 and 1 are the same, so I'm just going to cross that off. All of these guys, calculating my formal charges, have a 0 charge. In this structure for number 2, it has a negative on the oxygen and a positive on the carbon. In the structure number 3, it is a positive on the oxygen and a negative on the carbon. So now what we need to do is figure out which structures are the most desirable. So looking at this, number 1 has 0 as an overall, everybody has a no formal charge. So this would definitely be your ideal one. Okay, so that's your number 1. Then we have a comparison of between 2 and 3. In 2, the negative is on the oxygen, and in 3, the negative is on the carbon. Well, oxygen is more electronegative, so we're going to want that charge, the negative charge, to be on that oxygen. So number 2 would be the second most stable or more desirable, meaning it would be found the second most often out of these 3 choices. And then comes your third one. All right, trying the last one. We have SO4 -2. If you look down, well, let's do all the different structures. I guess I'll draw them out. So this is the first one, okay? All of these work that are being drawn down for you, all of them are absolutely okay because they follow the number of valence electron rule, and they all have octets or an expanded octet because sulfur is okay with that. So what we're going to do is we're going to compare, though, all of the different structures. I think I'm going to go with yellow. So if we have this, okay, this is another possible structure where you have sulfur with 1 double bond, and then all of the other oxygens have single bonds, -2. All right, looking at my overall formal charges, I've got a +2 in this guy and a minus, 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 minus on all the oxygens. So overall, as far as electronegativity goes, it's good that it's on the oxygens, but if I count, I have 5 formal charges, okay? If I look at my second structure where I have 1 double bond, okay, calculating how many their formal charges, this oxygen has a 0. These guys all have -1s, and then sulfur in this case has a +1. So looking at this, even though once again all of the oxygens have the negative charges compared to the sulfur, this has 4 atoms with formal charges. So in relationship, the second one with the 1 double bond is more favorable than the first drawing. If we look at these guys down here, these oxygens with the double bonds have 0 as their formal charge. We have a -1 and a -1 here, and sulfur has a 0 formal charge. So looking at this, I have 2 elements with a formal charge. Okay, which means that this is the most favorable. If we look at all of these structures down here, they all have the exact same 2 formal charges, and they're all on those oxygens. So these are all equally favorable. Okay, but when we look at, when we're asked about all of these things, this would be your most favorable. That second one with that double bond that I just erased would be your second most favorable, and this would be your least favorable because everybody has a formal charge. All right, hopefully you kind of have an understanding about how to do resonance and formal charges, and have a great evening.